Okay, thank you. So in this section, as Jason mentioned, we're going to cover how to accelerate gem5 simulation with using KVM to fast forwarding and also checkpointing. So gem5 is slowed, so but like it's not our fault. It's the natural of simulation. So fortunately, there are some workaround. We don't need to simulate everything perfectly or at all. Simulations can always be made faster by simulating less. Like this is not always a bad thing. Large part of the simulations are not interesting to us, such as the kernel boot and the wider OS setup, or when the benchmark is initializing, or at the end after our ROI when it's finishing and cleaning up. We don't care about it at all. So our goal is to just run the regions of interest in detailed mode. How do we get to the region, the ROI fast? We can use KVM to fast forward, or we can take or restore a checkpoint. So fast forward with KVM, as Jason mentioned in the core section earlier, KVM is the kernel-based virtual machine. It used the hardware visualization extension. And Gem5 used the KVM as the CPU model to fast forward the simulation, and it's fast. So things to be aware of when using KVM to fast forward is that the guest ISA must match the host ISA. And the M5 op and annotation must be in address version. So, so we have an example on how to analyze the address version of M5 op here, but since our time is kind of constraining, we're not going to actually do the example, but we're going to walk through this. So as we saw it in the morning, the instruction version of the M5 op annotation couldn't run in host. It would encounter the illegal instruction core dump error. So in order to use the address version of the M5 op, we need to open the def map file during the process and set up a magic address range for triggering the gem5 operation. Note that there's default magic address for x86, which is the first one, and the ARM64 is like that second one there. So of course, like as many things in Gem5, we can config this magic address by changing the M5 ops base address in the system sim object. And the source code of that can be found under source sim system.py file. One high-level example can be found in the x86 board in the standard library. And you can go check it out if you're interested. So we're also in this example here, which we're not going to go through, but I'm going to walk you through. So this morning, when we do the annotation for the workload, we need to include the gem5 M5 op header file. If we want to do address version of M5 op, we also need to include a header file that's called M5 mmap. This contains the function we need to open the def map file and also change the M5 base address. So then we can use the M5 op address variable to store our magic address and use the map M5 mem function to open def mem to map our magic address range into the def mem of the process. So just like we did in this morning, we need to call the M5 op function to trigger this M5 ops. So in address mode, we need to add the underscore address behind the function to trigger the address version of the M5 ops. And at the end, we can unmap this address range by calling the unmap M5 mem function. So in the compiler command here, beside the one that we need to add, for the instruction version of M5op that we did this morning, we also need to add the util M5 source directory to the compiler's include search path, and also add -nopy to not make a position-independent executable. So for our makefile, it will look something like this there. Is there any questions so far? Okay. So if we run this address version M5op annotated program on the code space, we will find that it will not have the illegal instruction error anymore. So which means which means that we can use it with the x86 KVM. So let's do an example on how to run a KVM script in gem5. So for this example here, we'll run the class A EP benchmark in the MPB benchmark suite. So gem5 resource provides us with the MPB EPA workflow that allows us to run it with a single line, which is board.set workload, obtain resource of the MPB EP-A. So we don't need to worry about building the disk image, the workload, and annotate them for now. So in this workload there will be M5 work begin address call after the EP's benchmarks initialization, and M5 work end address call after the EP's ROI finish. So we can look at the source code of it later. So for this exercise, all the material can be found under material 02 using gem5, 08 accelerating simulation, and 02 KVM time. So our goal of this exercise is that we want to use KVM to fast forward the simulation until the beginning of the ROI. Then when the simulation reaches the ROI begin, we want to switch our CPU from the KVM CPU to a timing CPU. Then we dump the stats so we can look at it later, and reset the stat before collecting meaningful stats. And after that, we schedule an exit event so the simulation can stop earlier for us to look at for the detailed stats. Then after this, we'll fall back to the detailed simulation, and at the end, we can look at the detailed stats. So let's go to the directory. So in here, this is our script. So the thing lacking here is a processor and a work begin handler, and we also need to set up the work begin handler with the simulator module. So let's fill them out. So for the processor here, we're going to use the simple switchable processor, which allows us to switch between or switch from one CPU type to another. So let's write it here. So we will set up our starting core type as a KVM type CPU. And our switch core type as a timing CPU. And our ISA is the x86. And we're going to showcase with 2 cores here. So for our work begin handler here, we wanted to dump the stats at the end of the KVM fast forwarding, switch the CPU type, reset the stats, then schedule an exit event after about 1 millisecond, which is 1 billion ticks, and then fall back to the simulation. So we can do this by using the M5 stats to dump. our stat here. Then use the processor dot switch function to switch our CPU type. Then we can use simulators set max tick. Function to schedule a max tick XA event, which we want it to be 1 billion here. Then we want to use the M5 stats to reset the stats before collecting meaningful stats. Then we yard false to fall back to simulation. And we can have some printing here to let us know what's going on. After this, we need to use the onXA event parameter to to set up the handler for work begin XA event. So let's try to run this. Okay, so with the dash RE option there, it will pipe the log and the error message to the sim out inside the gem5 output directory. And as you can see, because it's the first time getting the resource, so it will take some time to download there. So while it's downloading, we can look a little bit on what the workload actually annotate in here. So this is the source code of the EP. So as you can see here, there's a M5 work begin interface call right before our ROI, which is like right after the initialization of the benchmark. And after the ROI, there's another M5 work and interface that's called right there. And this is the one that's raising the M5 work begin and M5 work end XA event for our example here. Okay, so it seems like it finished running, but oh no, it just started. Sorry. So for dash RE, we can look at like what's going on in the terminal with the board.pc.0m_1.device file. But yes.
We ran out of disk space.
Oh, we ran out of disk space? No, no, this is the perf. Like.
Well, okay, we're gonna run. The reason why it disconnected is because we ran out of disk space.
Oh, I see.
Can you? Keep talking.
Okay.
If you have something to say.
So we are seeing the panic there is because like for some kernel, we might not have the permission to use the perf for KVM CPU. And later we will show an example how do we like disable like our KVM CPU to use the perf so that we won't run into this panic.
Better. Okay.
Yeah. Okay. Thank you. In order to avoid this panic, we can in here use the get the core from the processor. since we need to disable it for the KVM core, and the KVM core is the start of the switchable processor, so we can get it from processor.start. And in process core use perf. So with this, we will disable using perf for the KVM CPU. Yeah. So let's run it again. It's taking longer than I thought. Okay, so it started running, and we can see all the terminal log in this board.pc file under the gem5 output directory here. So if we scroll down, this is all the booting message for the kernel. And if we scroll down and see this, it means that we reaches the ROI begin that we annotate for our EP workload. So it also means that we should encounter the M5 work begin exit event and print out and fall into the handler that we just defined there. So so now the simulation is done, we can look at the stats file really quick. So I think we should first look at the stat file for our KVM core. So remember, there's two stat dump in our simulation. The first one is when the KVM reaches the ROI begin, and we did one stat dump, and the other is the timing CPU reaches 1 millisecond, and we did another stat dump. So if we grep for the board processor start. If we look at all the committed stats of our KVM CPU, we will find that it's all 0. So it means that any of the simulation stat that is done by the KVM CPU is meaningless. We should not use it, even though it would give us stats such as sim second. For the KVM part, we should ignore this and not use this. And also, yeah. So let's look at the actual timing CPU stat there. So the timing CPU, for switchable processor, the start stat for the core would name something like start with the index of the core. If it's a single core simulation, then it would just be start. But for the switch 2 CPU, it would be something that's named like switch with the index, or it just switch if it's single core. So in here, if we look at the switch stat here, we can see that for the first dump, it's 0 because it has not been run. But for the second stat dump, it's actually having the number of operations that's actually being run. So we can actually pick the stats that's actually done by the timing CPU. So there are some downside of using KVM to fast forward. So KVM fast forwarding requires the actual hardware KVM thread. So it means that it might constrain the amount of simulation we can run in parallel. And we need to spend time in fast forwarding for everyone with KVM. So if the fast forward region is large, it can still be time consuming. And the third one is that the simulated system has to have the same ISA as the host. And the fourth is not deterministic. So we can work around the above downsides by using the checkpoint feature in gem5, which we will cover tomorrow morning.